Alright, so in this video I'm gonna be explaining another important article with the title Domain Generalization by Learning and Removing Domain-Specific Features. As I said, we usually try to decompose our feature vector to domain invariant and domain-specific features. So this paper suggests that we should remove domain-specific features, removing this part. This paper in 2022. So deep neural networks suffer from domain shift when the test dataset follows a distribution different from the training dataset. Domain generalization aims to tackle this issue by learning a model that can generalize to unseen domains. So we propose a new approach that aims to explicitly remove domain-specific features for domain generalization. Following this approach, we propose a novel framework called Learning and Removing Domain-Specific Features for Generalization that learns a domain-invariant model by tactically removing domain-specific features from the input images. Specifically, we design a classifier to effectively learn the domain-specific features for each source domain, respectively. We then develop an encoder-decoder network to map each input image to a new image space where the learned domain-specific features are removed. With the images output by the encoder-decoder network, another classifier is designed to learn the domain-invariant features to conduct image classification. So we have n sub I number of samples in our domain. So in our source domain, we have different source domains, n capital the number of source domains. This is an overview that in A you will see here that it is the domain-specific classifier F1, F2, F3, Fn. It is trained with the classification laws on the source domain and the uncertainty laws, L of uncertainty, on the training source domains. After training, the weights of all domain-specific classifiers are frozen. In B, you will see that the encoder-decoder network is trained with construction laws and the uncertainty law through the domain-specific classifiers. Meanwhile, the domain-invariant classifier is trained with classification laws on the mapped images. And in C, you will see that in testing phase, the encoder-decoder network and the domain-invariant classifier are used for classification of target domain. So our framework starts by training any individual domain-specific features in which the classifier is designed to only use the domain-specific features from the source domain D sub S sub I to discriminate images. The domain-specific classifiers should not use the domain-invariant features as cues. In other words, F sub I is expected to be able to effectively discriminate images across different classes within the sub S, but it should be difficult for F sub I to discriminate images across different classes within any other domains. Domains excluding D sub S are used to maximize the classification uncertainty or adversarially increase the difficulty of classification. The classification performance of F sub I on the domain excluding D sub S should be similar to a random guess. So the classifier F sub I is trained by minimizing a classification loss. And maximizing the uncertainty, now here we have the uncertainty loss. We have seen this kind of thing in active learning, also in curriculum learning, model editing. There are many paradigms that use a similar technique because they are explicitly using this value of this loss, or even the prediction, the uncertainty, using the probability value, the value of the probability, not the final prediction. So it's very interesting. L sub u is the uncertainty loss, and then apply to the classification. So L sub s and L sub u are classification loss function and the uncertainty loss function respectively. We use the cross entropy loss as the classification loss. For the uncertainty loss, since we aim to make predictions similar to a random guess, we use the entropy loss. So this is entropy, P log P. And C is just a number of classes. Then we train the classifier to predict the least likely class. The least likely loss is L sub S, L sub C, where y hat here is the arg mean of y. Condition given f sub I. So after training, we freeze the parameters theta of these domain-specific classifiers and use these classifiers to learn domain-invariant features. Now here we are removing the domain-specific part that I said just remove it. To remove it, we utilize an encoder-decoder framework that maps the images into a new image space Z. The output images are fed into domain-specific classifiers F sub S and a new domain-invariant classifier. Unlike the training of domain-specific classifier F sub I, where the source domains is used for minimizing the classification loss, on the contrary, the source domain is used to maximize the uncertainty loss. So this parameter theta I are frozen, and the parameters of encoder-decoder are trained. Maximizing the uncertainty loss forces the output image Z to contain fewer domain-specific features than the input image. In doing so, the encoder-decoder network can remove the domain-specific features in the input images X and retain domain-invariant features in the output images. To maintain the overall similarity between the input and output images, we add a reconstruction loss for the encoder-decoder network. Now this one is the reconstruction loss. Again, it's very interesting that we are using the loss of reconstruction inside this loss to minimize it with respect to theta sub m. Because these parameters are the parameters of encoder-decoder network M. So we then train the domain-invariant classifier by minimizing the classification loss on the output images of all source domains. So theta f here are the parameters of the domain-invariant classifier. Then we train the domain-specific classifier and we get the loss. So when training domain-invariant features, we optimize this loss, L2. And then there are some theoretical work on putting some upper bound on the generalization risk for the target. This is target. This is for risk for the source, different sources, because we have n number of sources. And you see, these should be important factors that we should care about.